in the audience. Today I have the pleasure of introducing Dr. Derrick Lee. Derrick is from Newfoundland, where he obtained his bachelor's in biochem and applied mathematics from the Memorial University of Newfoundland. He then went to get his master's in stats from UBC and PhD in epidemiology as well as biostatistics. Recently, he completed his doctorate with SPPH and the BC Cancer Agency, where the focus of his dissertation was on examining environmental and genetic risk factors for breast cancer and whether genetic susceptibilities modify the fact of exposure. His areas of interest are biostatistical and epidemiological methods, predictive modeling, bioinformatics, and data mining and big data analytics. Currently, he is a statistical methodologist with cancer surveillance and outcomes at the BCAA, working on surveillance monitoring and cancer trends across BC. Please join me in welcoming Dr. Lee.
All right, testing. We good on sound? All right, perfect. Well, that's a little loud. We good? All right, perfect. All right, thank you, Raymond, for the introduction. So, as you said, I actually finished my doctorate through SPPH here, and talk today on modeling occupational polycyclic aromatic hydrocarbon exposure using workplace monitoring databanks with special applications to occupationally related risks for breast cancer. That was part of my doctoral dissertation, and interestingly enough, a big chunk of what I'll be talking today was actually done with a colleague of mine who actually came through the program here when you guys actually used to be called Zoe, and now he is a researcher over at Drexel University in Philadelphia. All right, so to give you a quick overlay of what we're going to talk about, we'll give you a little bit of background on polycyclic aromatic hydrocarbons. I'm simply going to call it PAHs because it's a bit of a mouthful. And so we're going to talk then about the health implications as well as how we're actually exposed to this particular carcinogen. And then we'll talk about how we can actually estimate pH exposure as well as the general scope of measuring them through what are known as job exposure matrices. And so when we talk about this, we'll actually break into two different sections. One talking about the idea of expert-based GEMs, so things where we use people like industrial hygienists to determine level of exposure. And we'll talk about our method that we developed, which was using empirical-based measurements from databanks. We'll then go into some direct applications and look at the occupational pH exposure and risk for breast cancer. And finally, we'll finish up with some of the significance of our findings. So, pHs and their health implications. So, several variants of pHs have been classified previously as being carcinogenic. And they are associated with several different sites, including lung cancer, bladder, liver, stomach, and skin. Now, the interesting thing, though, about pHs is they're not actually carcinogenic. It's actually their intermediate products that are carcinogenic. In short, essentially, pHs are inert. And eventually they become water excretable down the road. However, during the metabolism phase, though, it's actually when we actually create these reactive intermediates. And there are three such pathways. One such pathways end up producing what are known as radical cations, and as such, they end up damaging DNA. Now, the other two pathways produces what are known as diol epoxides or O-quinones. Epoxide, like the inset here, on the right side, that's recognized by their double hydroxy group with the O. And what they end up doing is forming DNA adducts. And what's basically causes and how this relates to carcinogenesis is these adducts end up skewing the shape of DNA. So down the road, during replication, transcription phases, that obviously can actually skew what ends up being produced. And that can end up leading to, let's say, mutations, to tumors, and so therefore carcinogenesis. Now, in terms of exposure, the thing about pHs which makes it very challenging is exposure is ubiquitous. And this is mainly due to the fact that pHs are actually the byproduct of incomplete combustion of fuel. So what that basically means is anytime we're talking about the burning of anything, chances are you're actually being exposed to PAHs. And so this can occur through a variety of sources. One of the main sources, ambient air pollution. If you're commuting, if you've ever ridden a bike, you've got stuck behind, let's say, a diesel truck, diesel engine, a truck of some sort, that very distinct odor associated with a diesel engine, chances are you're being exposed to PAHs. Smoking, secondhand smoke. Well, we already know that when it comes to smoking, you're being exposed to plenty of different carcinogens. But again, because we're talking about the burning of material, chances are you're actually being exposed to pHs as well. More surprisingly though, diet and cooking habits. If you've ever had barbecue, if you had a well-done steak, if you've ever burnt your toast and decided not to scrape off the black stuff, that black stuff has a component that is associated with pHs, so you're being exposed. However, what we're going to focus on today though is occupational exposure. Now, with regards to the first three, although the level is fairly low, the frequency of exposure is fairly high with respect to ambient smoking and diet. But when we talk about occupational exposure, the level is much, much higher. Now, exposure across industries and occupations can vary. Now, some of the common ones we can think about, things like industrialized industries, so petroleum refineries and so forth, because again, we're talking about the burning of fuel. Some surprising ones, garage mechanic workers and truck drivers, again, we're talking about the combustion of fuel. And the one that we found most surprising, restaurant workers. So if you've ever been to a restaurant, you see flames smoking up in the background, chances are people there are being exposed to pHs. And chances are this before a majority of your age, but before smoking bans were occurring in restaurants, people again were being exposed to PAHs. To give you some level of context, we can all probably agree that some place like Detroit, Michigan is fairly industrialized because it is associated with the auto industry. When we look at the air quality index, we find that the ambient concentration of pHs is somewhere less than 0.1 micrograms per cubic meter. However, when we go to things like a bitumen processing unit, which is associated with petroleum refineries, those levels are as much as 10 to 400 times the level of pH exposure. Now, when we look at ideas of exposure, we also have to look at the type of exposure. So we're focusing on chronic or long-term exposure, and that's exposure that is sustained over a prolonged period of time, as opposed to acute exposure, which usually occurs at a point of time or a short period of time. And the main reason behind this is because aside from, let's say, radiation or mesothelioma, it's not very often that you see the health impacts very immediately. Now, when we do focus on the idea of chronic exposure, things get a bit more difficult when studying, and that's mainly due to the fact that when you look at long-term exposure, the level of exposure can change over time. As well, the time span between exposure and diagnosis, as it increases, the chances for, let's say, changing in the job itself, or loss of records, or your recall ability does decrease over time. So, in terms of how we can actually assess these methods, some of the easiest methods are things such as self-reporting exposure. However, they do have their disadvantages, mainly due to the fact that you have to be aware of what you're actually being exposed to. Not very often are workers actually fully aware of what chemicals they've been exposed to or what materials they're actually handling. As well, again, changing of jobs over time basically affects the recall ability. Other methods are looking at occupational histories. Now, they have the advantage of basically being a long list of history of which we can reference. However, again, it has its disadvantages, such as the fact that job titles can change within industries, and a single title may refer to occupations in different industries with very different levels of exposure. Now, the thing about this, though, is the idea of looking at industry and occupation, they also have their challenges, mainly due to the fact that there is heterogeneous exposure between industries and occupation. Now, some of the traditional methods looking at only industry, for certain exposure, it's valid to just look as an industry as a whole. However, when we start to look at the occupations within the industries, it may be obvious that we can start dividing up our groups, that people such as the owners, secretaries, people who are administrative personnel, they may be slightly different or working away from people who are skilled workers or manual laborers who actually work directly with the material. And then logically, then, the level of exposure is going to be different between these two groups. So, in order to deal with something like that, we end up looking at slightly different methods, such as the job exposure matrices. Now, these are cross-classifications of industry-specific jobs. And what that happens is it allows us then to look at the job and industry and basically turn that into exposure data. Often, they're based on expert opinions, such as industrial hygienists, who will end up classifying the level of exposure. And they often give us some sort of ranking based on an ordinal level. And for example, you may get the values of 0, 1, 2, 3, which relate to none, low, moderate, and high. Now, one of the problems, though, with these type of methods is that, in short, this is basically a black box method, that the ordered values may be somewhat arbitrary, and that there may not actually accurately describe the difference between levels. If I tell you that one person is being exposed to a moderate level versus another person is being exposed to a high level, what actually differentiates that cutoff point? What happens if someone is just at the very top of that moderate level? Why is it that they can't be classified as high instead of being moderate? So, in order to deal with this, what we end up doing is we end up looking at 2 occupational data banks. And what this did is we end up using empirical data. Now, in Canada, there are unfortunately not many available resources on pH exposure. However, in the United States, there are several being maintained by the Occupational Safety Health Administration. And 2 data banks that we got access to, the first being the Integrated Management Information System. This actually contained more than 2 million records of various exposures collected by OSHA between 1979 and 2010. The other data bank is a very similar one, except that it actually had the raw data from the inspectors. And this was collected between 1984 and 2009. And when we end up amalgamating the data set and looking at pH-related exposures, we end up having over 2,500 personal time-weighted measurements of a pH surrogate known as coal tar pitch volatiles. We covered more than 750 companies across 45 states, and we end up using almost 500 different inspectors. The industries, we end up coding them to the North American classification system from 2007, and we end up using the 2010 SOC codes to classify the occupations. So, to produce something a bit more meaningful in terms of values versus some arbitrary ordinal value of 0, 1, 2, and 3, we end up modeling the likelihood exposure. And so what we did is, at the PL, the permissible exposure level, this is where the health impact of exposure levels this high may become detrimental. So we end up taking all the measurements and we simply dichotomize them as in exceeding the PL or being below the PL. And we end up using a logistic mixed effect regression model where we adjusted for year, industry, and occupation. And we used inspection number as a random effect. And we did this specifically so that we could adjust for the correlation of measurements across and within measurement sites. Now, through most parts, this is just a lot of numbers that isn't anything meaningful. So let's get to some actual data. So as we can see here, that across industries, there is clearly a heterogeneous level of exposure. When we look at something like, say, power generation or printing, there is a very low likelihood of exceeding the PL. However, when we look at something like wood product or metal manufacturing, we have a much more moderate level of exposure. And not surprising, when we look at, say, trucking and full-service restaurant workers, they have a much higher likelihood of exceeding the PL. Now, when we start to adjust, though, for occupations, now when we look at the minimally skilled workers, shouldn't be too surprising that through most parts, the level of exposure or the likelihood of exposure with the minimally skilled worker is actually going to be fairly comparable to those in the industry only. However, when we look at those individuals within the administrative personnel, those who obviously are probably going to be working directly away from the chemicals and are being indirectly exposed, the likelihood of exposure is much, much lower. So at the end, basically what we can say in terms of our takeaway message is that we end up developing several predictive probability models that first showed us that there obviously is a heterogeneous exposure across and within industries, and that it very much showed that occupations need to be considered when we actually examine exposure. In terms of what's usefulness, we basically provided some sort of estimate of occupational pH exposure that can be used to examine the exposure outcome relationships in terms of epidemiological research. Now, before we jump directly into the direct application, we'll just give a quick introduction to breast cancer. So, risk factors for breast cancer. As we said before with respect to PAHs, several variants are classified as being carcinogenic. However, the role in breast cancer is a little less clear, but we do have biological evidence to show that pH exposure may be associated with breast cancer. The first being the fact that pHs are fat soluble. and therefore they can actually accumulate in the breast tissue. We have evidence to show that breast tissue is capable of metabolizing pHs into those carcinogenic intermediates. And we have studies that show that elevated pH DNA adduct levels are associated with an increase in breast cancer risk. Now, breast cancer, though, has several other factors that affect it, with the most well-studied risk factors or established risk factors being the following: early menarche, so that's the first menstrual period, late menopause, and null parity. And the thing about these is all three of these are associated with modification to estrogen levels. Other established risk factors include obesity, sedentary lifestyle, and alcohol consumption. And again, all three of these are associated with the first three because, again, they do modify estrogen levels. And finally, to bring this back to pH exposure, pHs actually influence estrogen metabolism. So this feedback between pHs and estrogen in terms of modifying the effects of estrogen can be why pHs actually can relate to breast cancer risk. So to examine pH exposure and breast cancer risk, we ended up doing a joint study. And the study was between the BCCA and Queen's University. And it was a population-based case control that was conducted between 2005 and 2010. And at the end, we had a little more than 2,300 individuals. And importantly, every single one of our participants ended up doing a questionnaire that gave us information about their lifetime employment history. Now, to actually determine the level of exposure, we end up using 3 different GEMs. Now, the first GEM, this is based on the previous model we talked about. And using industry and occupation, we calculate the probability of exposure to excess levels of pHs. And again, emphasis is on the excess level. One gem that we ended up grabbing from this one here was from Europe. This one here, which was based on occupation, that gave us an intensity level, and that was based on some ordinal values from an expert. And finally, another expert-based gem, which used both industry and occupation. This gave us an intensity level and a probability exposure. Now, the reason I wanted to focus on the idea of excess levels is that from here with gem B, we're talking about the probability of exposure. So 0 means it's unlikely you're being exposed to. But with our model, we're talking about excess levels of exposure. So what that means is even though you could get a 0 probability of excess exposure, it does not necessarily mean that you're not being exposed to pHs. You're just not being exposed to a point where there are where the health effects can be detrimental. Now, at the end, we end up estimating the lifetime exposure, things such as cumulative exposure, the weighted duration, total duration, and average probability. For most of you guys, you probably are familiar with cumulative exposure, where you take the intensity, you times it by the duration, you then sum that up over all the jobs. We use this for Gem A and Gem B because they gave us some intensity level. However, because the ppm gem gave us a probability, we couldn't quite use the exact same value. So we ended up doing what's called the weighted duration, which essentially is the exact same thing as cumulative exposure, except now we take the probability of exposure, times that by duration, and then again add that up over all the jobs. For average probability, it actually is the weighted duration, simply divide by the total duration. And finally, total duration at exposure. Basically what that means is, let's say for example, we classify something as being a high risk of exposure. We just simply summed up the duration of those specific type of jobs. Now, to compare how much these methods actually agree with one another, we identified more than 3,500 unique jobs within our particular dataset. And we found that with respect to the ppm gem, about 40% were ever employed in some type of occupation where there was a high risk of exposure. And for our definition, we define high as being there's a 10% probability of having an excess level of exposure. With respect to our expert-based gems, Gem A and Gem B, they gave us around 25 and 20% of our subjects being ever employed in a job where there was some level of exposure. Now, to compare their actual level of agreement, what we end up doing is looking at the kappa statistics. So basically, to what level of which they agree with one another. So we compare right now the high level within the ppm gem versus our Gem A and Gem B. And as you can see here, the level of agreement is abysmal. When we look at the ppm gem, it's only about, well, barely over 10%. But what's interesting here, though, is that when we look at Gem A versus Gem B, these are both our expert-based gems. Their agreement is even worse. They're at 0.05%. Now, the nice thing, though, about the ppm gem, though, is that we can calibrate it because we're defining exposed based on some percentage. So what we end up doing here is we decide to look at both Gem A and Gem B and calibrate the level or threshold of what we define as being exposed based on the prevalence exposure within Gem A and Gem B. So to match Gem A, we basically defined that you had to be more than 71% likelihood of exposure to match their definition. And as we can see here with the capital statistic is much higher at 0.6. However, when we look at Gem B, though, it's basically null. There is virtually no agreement, and any agreement is strictly by chance. When we calibrate the ppm gem then to Gem B, which said that at 35% was a requirement to define someone as being exposed, right here again, when we compare against Gem A, it's not too bad, much higher than originally, now it's 0.34. But again, when we look at the comparison with Gem B, it's still relatively weak. So, why is that? There are several reasons why this can occur, but basically what we found was that at the very least, with respect to Gem A and Gem B, they're being much more specific than ours. Versus the ppm gem, we found that was a bit more sensitive. So clearly there are some differences that stem from who's being defined as exposed versus not exposed. Now, when we actually look at the industries, so right here what we end up doing is we want to look at which industries were actually being identified as being exposed. And as we can see here with the ppm gem and Gem A, food service industry, food manufacturing, and a mishmash of other manufacturing, these are the top 5 industries that are being exposed. So the agreement is not too bad. However, when we look at Gem B still has food manufacturing and a mishmash of other types of manufacturing, but food service workers aren't there. And in reality, Gem B actually says that food service workers are not exposed. And that's part of the reason driving why there's such bad agreement between all of our gems. So that there is, to a certain point, some level of misclassification within our exposure assessment. And that can be problematic because when we look at this particular data set, we found that more than 20% of our women had at some point in their history worked in the food service industry. Unfortunately, this does bring into question how do experts actually devise ways of defining who is exposed versus who's not exposed. And this is especially challenging when there are differences in opinions. And unfortunately, the majority of this stems from the fact that most of the industries that were studied by these experts were male-dominated. And that the industries that women worked in were often very different from the ones that were actually being studied. And so this highlights the problem when we look at expert-based judgment that are using inappropriate samples. And unfortunately, we may have some level of gender bias being devised in these expert-based gems. However, despite the fact that the agreement is fairly low, we were still able to actually find some level of association with breast cancer. And when we actually looked at our expert-based gems, we actually found elevated, although non-significant results that showed there was a relationship between pH exposure and breast cancer risk. And when we looked at the ppm gem, we actually found significant trends with breast cancer risk. That when we looked at either the highest or longest categories associated with our 3 calculations for breast cancer risk, we found odds ratios between 1.3 to 1.5. Now, when we actually then looked even further and we started to look at some of the sub-analyses, we did find that unfortunately there was no association when we looked, or no differences when we looked at, say, hormone receptor status or some of our basic demographics such as ethnicity, SCS, and BMI. We also found that there were unfortunately no significant differences based on menopausal status. However, we did find that the effects were slightly stronger within the premenopausal group. And finally, when we looked at family history, we actually did find evidence of some interactions with family history. Now, the focus on those last 2 points, and looking at the premenopausal, previously we found that with the main effects, the odds ratios were about 1.3 to 1.45. Yet when we look at the highest level, it actually is much higher at 1.75. And more staggering was the fact that when we looked at first-degree family history, the levels almost doubled, at that the highest or our longest level is at almost 3 times the risk of developing breast cancer. So, in summary, we found that prolonged occupational exposure to pHs in jobs with some level of exposure is associated with an increased risk of breast cancer, and that pHs may have stronger effects in women who are premenopausal or have first-degree family history. And the fact that within the people who had first-degree family history, that the odds ratios were that much larger gave us some indication that there may actually be some effect modification or interactions between genes and breast cancer risk. So, to summarize the significance of our findings, we end up developing several predictive probability models that can be used for a variety of epidemiologic studies, as well as ways in which we can assess exposure compliancy within industries. When we compared our GEMs, we found that obviously there are and can be some issues between expert and even empirical-based measurement methods, and that unfortunately there may be underrepresentation of industries and occupations in which women may dominate. And therefore, when using these type of expert-based methods, considerations should be made when we're using older GEMs within certain populations in terms of its ability to capture exposure. And this is one of the advantages of using an empirical-based method, is because down the road, the ppm gem can easily be updated. So we can look at either historical trends or when more industries and occupations are measured. In terms of the applications, we found that when we analyze our breast cancer risks, we found that prolonged exposure is again associated with increased risk of breast cancer, and that the effect is particularly strong among premenopausal and those who have family history of breast cancer. And finally, our research adds evidence to the role of occupational pH exposure have on breast cancer risk, which can be used to improve exposure and preventive measures, and finally, gives us a greater understanding of the etiology of breast cancer. Thank you.
Thank you, Derrick, for that. At this point, I'd like to open up the floor for questions. Does anyone have any questions?
Thanks, Derrick. That's really excellent work, and hopefully a good introduction for the newer students in the class to the idea of the job exposure matrix and what it can do and what its limitations may be. Can you talk a little bit more about the source of the data in the databases that you used? You said there's 2 million observations in there. Is that correct, in the OSHA database?
So within the IMIS database, which that one there's now, actually that one is now freely available. When we originally grabbed it, which was back in 2012, it wasn't freely available, and so we actually had to do an Access to Information Act to actually gain access to it.
Okay, but where did those data themselves come from? So is that all OSHA inspectors and data that they have collected over time, or does it come from individual epidemiologic studies? Is it a collection of data from a bunch of different places?
So with all the OSHA databanks, they're basically a compliance measurements. So basically OSHA is, I guess, the equivalency to WorkSafe BC and I think CARWA is the other one here, or is that just the general agency?
Fair enough.
Okay, but anyway, so basically what happens is that they're like WMIS. They basically monitor all types of exposure out there. So sometimes when people have reason to believe that there is someone violating or being non-compliant with exposure levels, they can send inspectors there to basically do some sort of testing. Sometimes it's through requests, sometimes it's through surprise inspections. And obviously at this point in time it's been collected through, at least in terms of data banks, more than 40 years. In terms of the exposures, this is across the board. And so it may vary. The amount of data and the quality data can vary depending on what type of exposure you're looking for. So within the particular data banks that we had access to originally, we had information for pH exposure, there was information on wood dust, information on formaldehyde, as well as a variety of other types of exposure. So these type of data banks are definitely a wealth of information when you want to look, when you want to basically explore historical trends, or in our case here, produce some sort of model that looks at the likelihood of exposure.
Okay, thanks for that more detailed. explanation. One of the online questions here is, has there been any new research that uses exposure classification in line with the AIHA classification to standardize the GEM process?
Sorry, can you repeat that one more time? Sir.
Has there been any new research that uses exposure classification in line with the AIHA or American Industrial Hygiene Association classification to standardize the GEM process?
To my knowledge, I've not heard of anything about anything like that. And unfortunately, my doctoral work is basically a mishmash of several things. So I've been looking at occupational exposures, I've been looking at genetic aspects, and I've been looking at statistical modeling. So I'm only lightly scraping the surface of occupational work. With that said, though, I wouldn't be surprised if something like that would be of interest. But the fact of the matter is that when we look at these type of GEMs, because we have such varying opinions to try to look at any type of exposure, in general, unless it's like the way IARC does it, where you have massive meetings and several people collaborating together to unify our list of, in this case with IARC, the list of what is being classified as a carcinogenic, to develop one type of GEM for one particular exposure would be incredibly challenging.
Okay, I have another tough question here from online, and then I'll hand the microphone back. It's, what was the rationale for selecting the PEL as for the exceedance model? The PELs are quite outdated. Did you consider using any lower cut points, or did you try any lower cut points?
We did consider different cut points in terms of modeling, but the main reason is just because, unfortunately, and that's something that you guys will probably deal with in your own work, is that there are traditional methods of when you look at any type of analyses. From a statistics standpoint, why do we use 0.05 as a p-value as our standard cutoff? There is no logical reason behind that. Recently, even the ASA came out against using that value. But in terms of simplicity, in terms of having something that is tangible and understandable to everyone else, that's why we use the PEL value.
So I think that question was around the 200.
Yeah.
Okay.
Yeah, so that's the reason why we use 200 micrograms per cubic meter, because it's something that has been established. There is, obviously, because it is outdated, it may not be as relevant now, but we want to use a less arbitrary cut point, because especially when you look at any type of categorization, trying to justify the cut points is incredibly hard. So this is why we use that one, because it's something that's a value that is understandable.
Hi, very interesting presentation. I had a question about the method that WorkSafe BC would use. So if a individual comes to them and says they're diagnosed with breast cancer, what method does WorkSafe BC use to determine compensation for that worker, and what are the implications for your findings for a workers' compensation board? Thank you.
Unfortunately, I don't know the intricacies or how Workplace BC does these type of things, so I can't come close to actually answering that question. The only thing I can state that I guess in some level comparable to what it is that I probably would end up looking at how Denmark has done things. So recently, the idea of LAN and late night and its association with breast cancer, it has been around for about 20, 30 years now, and only recently has it become to a point where it's being recognized as being a risk factor for breast cancer. And if you look at Denmark as a pilot study, they've been doing it where now women who have no history of breast cancer, who have no breast cancer, have no family history of breast cancer, if they end up developing it and they have been working in industries where light at night is a risk factor for more than, I think it was 20 years, then they go through the compensation process. So I would probably end up looking towards them to guide us at this point in time, given this is very new territory.
So one of the fascinating aspects, I think, of what you've done is this question around different job categories that might not get sampled necessarily because of who works in them. So you came to the conclusion that the food industry or the food service industry was underrepresented. Do you think there's other industries where PAHs are likely a problem, that are sort of predominantly women working in those industries, that might not be well represented in the data set you've used?
As a general statement, I would say that although I love what we've been able to do with the OSHA databanks, they're nowhere near as encompassing as it could be to actually grab pH exposure. One of the challenges is the fact that with respect to pH exposure, there are a lot of different sources. And so things such as like OSHA and these type of databanks, they're looking at, in this case here, fairly industrialized industries in terms of actually looking at the measurements. But as I pointed out, and as Sarah just mentioned, is that there are places where it's underrepresented. And the thing about it is that when they were measuring it, they were looking at, so let's go to the extreme example and look at something like a petroleum refinery. So you look at someone like at a bean processing unit, and you basically either take a personal measurement or you'd use this little tube near them, and it'll collect the sample and so forth. But there are people who are still being exposed to it that may be away from it, such as, again, people who are administrative personnel. Now, if we though look at historically, and we look at something like more than back in the 50s, women were being exposed to pHs, but they were never actually, we would never actually monitor those type of jobs. And one of the interesting ones that I found recently was when we look at telephones. That back in the 1940s, 1950s, 1960s, when smoking was a very, very common thing, a lot of people would literally just be at their workplace smoking a cigarette, being exposed to pHs, but we would never consider monitoring those people or actually obtaining those measurements. And in those cases there, let's say with the phone industry and the, I forgot what the term is, but operators, when they're plugging people in, again, they're being exposed, but never would we actually measure them. And so there are definitely a lot of industries and a lot of occupations where women are being exposed that through most parts, something like OSHA will never actually monitor.
I think you mentioned in some of the job assigning low, moderate, high. Some of the processes used expert judgments, and you said that there might have been some gender differences in terms of not quite understanding the expert not quite understanding the job that was predominantly female occupied, and that it was mostly done by females. Can you speak any more on that topic?
In what specifically? I guess it's a kind of an open-ended question.
I guess like, have you seen that in other places where that inconsistency perhaps that you've seen in terms of job classifications and the misclassification because of that issue?
Well, without getting into too much detail, the biggest problem that we observed, at least with the Gem A and Gem B we were looking at. So with respect to Gem A, it did consider food service industry as being exposed to pHs, whereas Gem B did not consider it being exposed. Now, one of the issues right off the bat is age. Gem A was based on information that was coding from 1968. Gem B was based on coding from 1980. So right off the bat, we're now comparing two gems that are historically at very different time points, where one was based on a time where women in occupations wasn't as high, and with the other one at a time where women moving into the workforce was becoming more prominent. But in general, the biggest challenge with any type of expert, I find anyways, with any type of expert-based gem is because it's a black box method, we're honestly relying on their opinion. And if what their opinion is based on information that is no longer up to date, it obviously can skew things. And one thing that Nair talked about was, so the ordinal rankings of intensity level. With Gem A, it used the values of 0, 1, for Gem B, it used values of 0, 1, and 2. This represented none, low, and high. So they didn't bother doing a moderate. Now with Gem A, they also did a low, moderate, high. However, they actually used the values of 0, 1, and 4. So now they're putting that level of high much, much higher in comparison to low. And so when you calculate something like then the cumulative exposure limit, cumulative exposure, now the high groups are essentially 4 times the weight of the low group. And so we asked them directly, why did you do this? And despite the fact that we know these researchers, they honestly could not give us a good reason. It simply was that we believe that these jobs are so much higher that the weighting value of their ordinal value should be at value of 4. Now, it's not the best answer, but again, these are experts, so we have to assume that they're right. But based on what we're seeing here from empirical evidence, from actual monitored values, clearly there are some differences right off the bat.
Why did you model probability of exposure over the PAL rather than the actual exposure?
Okay, so there's a couple reasons behind that. One is the fact that because of the data that we're dealing with, there were, and you guys probably either experienced it, seen it, or read about, that there's something called the limit of detection. So a lot of times when the device you're using doesn't have a particularly low limit of detection, what do you do with all those essentially blank values? By dichotomizing it, at least removes that chance of, well, what do we do with the data? And you don't often, when you do something like a complete case analysis, where essentially you throw it out, you're introducing bias to your data. So we try to deal with that potential bias by using that cut point. Now, obviously, when you use a cut point, you also introduce a different type of bias because you're losing now information. But we found that due to the fact that there was 25% of our data was essentially missing due to the limited detection, it was a better trade-off than anything else.
Good old limited detection.
Well, okay. Well, thank you, Derrick, for that very interesting presentation. Once again, I'd like to thank Derrick, and if you guys could join me in giving Derrick a round of applause.
It's been,
You can turn yourself.
yeah, it's been interesting and challenging.